Welcome everyone to our SMA workshop. Thanks for coming. We have had quite some trouble organizing it, of course, during these times. Would have been nice to welcome more people, but that's the current situation and that's how it is. And I think we'll just make the best of it. The language will be English. I hope that's okay for everyone. We will record the presentation. There is a camera up there, so we'll have recording of the slides and of the people talking. Not of the audience, so I hope that's okay for everyone. You can get the link to the recording afterwards, and you can also get the presentation slides. I also promised that already to people who could not make it, who could not be here today. Very good. Then, another important point. Unfortunately, we just realized that we cannot have the apéro eating in here. We would have loved to do that, but due to the carpet, apparently it's not possible. So after the presentation, we can still chat and have a look at the demonstrators, but the apéro will be 100 meters across in the winter garden. You can always come back, but you should not eat in here. All right, then what's left is to welcome you again to the workshop. It's organized by several partners that were working together in a research project and an Interreg project between Switzerland and Italy called InnoSMAD. We have CNR from Italy, we have TSS from Italy, TSI from Italy, TSS, two companies, and Cscm from Switzerland. They will present themselves in detail, and I hope you enjoy the presentations, and I hope you'll take the advantage to get in touch with the people, to have a discussion, and to ask your question, and to see for yourselves whether what is presented here could be used for you, whether you could make use of these very interesting materials. Thank you very much. And then we'll start with Elena. Unfortunately, I don't have any.
Oh, no problem. Good afternoon to everybody. I'm Elena Villa. I am the coordinator of Sma Product, which is an Interreg project between Italian partner and Switzerland partner. And the principal argument of the Sma project is the investigation of the damping properties of the shea memory alloys. Particularly in this afternoon, we want to show the results of our project and then to communicate about the shea memory alloys, about also all the possibility to application of these particular materials. And only 2 words about our institute. We work in advanced alloy research, and we prepare the material, we work the material, and then we characterize all the innovative alloy. Particularly, our interest is devoted to the melting, preparation from powder also, traditional preparation and also from powder, microstructural physical characterization, study of working process, and advanced manufacturing. And so device development and application. The principal field is related to the shea memory alloys, but also the ferromagnetic shea memory alloys and the thermoelectric materials. My aim in my presentation is only to introduce in the shea memory alloys. Which is the shea memory alloys? are the Sma materials are the alloy which have a particular functional phenomenology. First of all, the shade memory effect. This is a whole video, but where we can deform material, in this case a spring, and then when we put the spring in the water, in hot water, the spring recovers completely its initial shape. The second principal phenomenology is the superelastic or pseudoelastic properties, where springs in nickel titanium alloys could be deformed in very high deformation, and then when I remove the stress, the springs recover completely its initial shape. This is the two principal effects that are related to the shade memory alloy. This is the only theoretical aspect that I introduce here. Why the shade memory alloys can show shade memory effect and superelastic or pseudoelastic effect. These effects are due to solid-solid transition, named thermoelastic martensitic transformation. This material can give from parent or austenitic phase to martensitic or martensite, martensitic phase or martensite. The austenitic phase is a high-strength mechanical phase, and the martensite is very deformable, very easy, weak mechanical material. And then when the material go from parent phase to martensitic phase or reverse, can show these particular properties. This transition could be induced by two driving forces, by the temperature, and in this case we have the shade memory effect, or by the stress. In this case we have the superelasticity or pseudoelastic effect, which is related to thermoelastic martensitic transformation and shade memory effect. This is the schema to understand these functional properties. We can start from austenitic phase at high temperature, and then we reduce the temperature, and the thermoelastic martensitic transformation occurs. And then in B, we have the martensitic state. The martensitic state at low temperature can be deformed by applying a stress, and then we have the twin martensite, the deformed state of the material. And then when we increase the temperature, the material recovery this initial shape by the transition from martensitic state to austenitic state. There is a two driving force, temperature and stress. This is the reason because this graph represents the change of temperature of transition when we apply the stress. The stress and the temperature are completely related in this phenomenon. And when we consider the shade memory effect, we have to consider four temperatures: martensitic start, martensitic finish, austenitic start, and austenitic finish. And there is four temperatures which describe completely the shade memory effect. When we consider the pseudoelasticity, the phenomenology is related to the inducing the thermoelastic martensitic transformation in isothermal condition, only applying the stress. In this case, we start from austenitic phase, and then we go to the martensitic phase, only applying the stress. We apply force, the material transforms, go to the martensite, deform in the martensite, and then when we remove the stress, the material come back to the initial shape. The martensitic state shrink, and then we come back to the austenite. In this case, we don't use the temperature, we use only the stress. But there is, in any case, a transformation. And this is the typical representation, the curves, the typical flag-shaped curves is the representation in stress-strain curve of this phenomenon. We have the elastic deformation and then the plateau which correspond to the transformation in martensite. And then we have to recover in a loading plateau to the initial austenitic phase. Also in this case, because there is two driving force, also in this case this phenomenon is related to the temperature. Because when we consider this deformation, at different temperature we have different critical stress. The stress and temperature are in any case correlated. Okay, this is the core of the function of this material. This is the transformation which can work in shape memory effect and in pseudoelastic effect. Starting from these particular properties, we can consider how we can use the shape memory effect and the pseudoelastic effect of this material. We can use this effect in, as we want shape. We can use wire, ribbon, spring, snake-like spring. We can prepare my material in very different way. In this case, also we present also some example obtained by selective laser melting, for example, and we can modulate the response of the material in shape memory effect or also in pseudoelastic effect. The pseudoelastic effect can be used in all the configuration, tensile, torsion, flexion, compression. In any case, we have the typical flag-shaped curves with different kind of plateau, with different kind of stress or strain, but this material can be used in any shape and in a lot of applications, starting from artistic application. This is a sculpture in jewelry or orthopedic device and so on. We only have to consider that we prepare the material to use which kind of driving force. If we use the temperature, we have to use small mass, small weight of the material. Or we can use the pseudoelastic effect. We can choose very, very open possibility of shape. The shape memory effect. Now we consider the principal parameter, the principal characteristic for use the shape memory effect. The shape memory effect can be used in three different ways. First of all, in free recovery. Simply the material recover its initial shape in free condition. This is the case of the application in design, in smart light, or in switch, which simply move from martensitic and austenitic phase without any force expressed. The second kind of application is recovery against a fixed strain, and then we can open the possibility to different junction, connection, tube connection, ring for contain to part of device, of a tube, and so on. And the particular properties of the shape memory alloys is that when we deform, for example, the ring, and then we we increase the temperature of the ring closes, and try to recover initial shape, but against the fixed strain. And then the ring continues to apply force. This is not a static junction, it's an active junction. The last possibility to use the shape memory effect is in actuation device. The material recovers its initial shape against changeable force. For example, the principal theoretical example are the recovery against weight. In this case, the wire move, the wire in austenitic phase by applying a load, deform in martensitic phase, and then when we hit the wire constrain, reduce its length and then move the weight. This is the theoretical example for, of recovery with fixed force. In this case, there is the module used in a a lot of application, valve, pump, and so on, is the two spring combination, one spring in shade memory alloys and one spring in steel, for example. When the memory alloy lower its temperature, the steel springs deform the shade memory alloys. And then when the shade memory alloys heat, increase its temperature, recover its initial shape, moving the steel spring. In this case is the principle of the basic actuator. And the maximum possibility to use this material in a very compact and simple way is use this material in shade memory effect in actuator and sensor properties. The material is heated by the environment, and then when the environment go to precise temperature, the material is activated and then move in actuator system. In this case, one springs and steel springs is used in place of thermocouple, motors, and so on. It's very compact and easy device. How can use the pseudoelastic properties? I use in isothermal condition and constant force. So we can use this particular elasticity of the material in a different field. For example, for the glass, for the biomedical application, the stent, the orthodontic wires. Now is very open the possibility to use the pseudoelasticity in devices, surgical devices, for endoscope application. One interesting and very recent application is the Elastocaloric Effect. When we consider the pseudoelastic deformation, we consider the flag shape cures. And in this case, when we have the loading part of the cures, the material transforms in martensitic state and release heat. And then when the martensitic state comes back to the austenitic phase, the materials absorb heat. Then we have a material which, by deformation, release and absorb heat. And then the first possibility is to use this material like a principle for a refrigeration system. From one point, the material absorb heat, and from another point, release heat. We can move and we can use the material in like the gas compression system. When we increase the pressure of the gas and we release the compression of the gas, we have absorption and release of the heat. Okay. Okay. Last application, but very interesting application, which is the aim of our project, is the damping properties. The damping properties origin from all the effect of the shade memory alloys, the martensitic state, but also the pseudoelastic effect. Because in the martensitic state, we have this particular microstructure constituted by twins and so on, and this particular microstructure damp the low vibration of high frequency and the low strain. but also is a structure useful for shock absorber because the materials the alloy can deform, absorb the shock, and then we heat the material, we recover the initial shape. Is a shock absorber useful for more cycling of work, is not for one cycle. The pseudoelastic properties are another point from damp the mechanical vibration, because we consider in this case high strain of deformation. By this particular curve, we have all this energy, mechanical energy dissipated in mechanical hysteresis. And then we have also the recentering properties. The material deform, complain the deformation, and then recover its shape, recenter the structure where it is applied. Which kind of alloy we can use for shape memory? A very different kind of alloys. The principal, we can consider two principal family for shape memory alloys: the copper-based shape memory alloys and the nickel-titanium-based shape memory alloys. The copper-based is interesting, particular for high temperature application. In this table you can see the transformation temperature and then the possibility to use this material in particular range of temperature. The transformation hysteresis, which is the parameter useful for the application, and the principal material which can express interesting properties, reliable and important for application are the copper-based, and the principal is the nickel-titanium system. The nickel-titanium system is the most used and now is the quite only alloy present in the market and produced and applied in very wide range of application. There is the ternary system also derived from the nickel-titanium, nickel-titanium copper, hafnium for high temperature, niobium for particular pseudoelastic properties. And then the last categories of alloy are the ferromagnetic shape memory alloys for multifunctional properties. And for this alloy we are still in research field, and there is only some prototype for application. This is another schema for the principal shape memory alloys. The nickel-titanium show very good properties. The strain recovery to 8%, the big stress developed for 400 becapascal, and high corrosion resistance, then biocompatibility. And these properties open all the biomedical application and a good workability. Now the producers are very prepared to offer to the market all the size for thin wire, for ribbons, but also for tube, for example, and so on. When we have to choose the nickel-titanium alloy, we have to choose the range temperature for the application, and then we consider the particular composition of the nickel-titanium. This system is very open because changing the temperature, the chemical composition, starting from, for example, the atomic composition of the nickel 49 to 51.2, we can move the temperature about for 100 degrees. then the control of the chemical composition, the control of the microstructure of the preparation of the nickel titanium alloys is very, very important to develop the application. Then, this is the nickel titanium chromium for particular high performance superelasticity. Okay, I think now we have the field, the principal consideration for the shape memory alloys, the physics base for the functional properties, and then the principal system I used. I thank you very much for your kind attention, and I am available for any question. Thank you. No question, Francesca, show all the part.
Good afternoon. I'm Francesca Villa from the National Research Council of Italy in ICMAT Institute. And in this presentation, I'll talk about the design and implementation of smart solutions with a specific focus on practical examples and applications. First of all, it's important to state that shape memory alloys are functional and smart materials which are very versatile, so they can fit a huge amount of different applications in different fields. However, it's important to point out that there are few reference standards, and also the modeling of their behavior, it's quite complex, so it's not so easy to know their behavior before designing. So it's very important to rely on practical experience and design guidelines typical of shape memory alloys. When you have to design a solution with shape memory alloys, the main parameters are the working temperature of the device or the component, because we have seen that the shape memory alloys properties depends on the temperatures, and since the transformation which gave the functional properties to these alloys is strictly related to the temperatures. Then the other important parameters are the stresses and the strokes involved in the specific application, because they define the level of force and strain that the Sma component has to exhibit. Then the other parameter is the required functional properties that are the shape memory effect, the superelasticity or the damping, and so on. Then another important thing is the cycling, so the duration required for the application, and also environmental requirements. When you have to design a technical solution with shape memory alloys, it is essential to know what you want, how to ask for it, and how to check that you got what you wanted and what you expected from this material. And in the light of this, the four main steps of the design with the shape memory alloys are the choice of the material and the specific composition, the choice and obtain the desired thermomechanical state of the material, the shape and the dimensions of the component, and finally the characterizations in order to check if the properties of the material are the one desired. The first step is the material selection, as Elena showed you before. There are plenty of alloys which show shape memory effects or pseudoelasticity, and the transformation temperature ranges are quite different depending on the kind of alloy and the composition, as Elena showed for the nickel titanium. And the main studied and used alloys are the nickel titanium and also copper-based alloys. Here you have an overview of physical properties, but the most used and the most developed system is the nickel titanium system, thanks to its outstanding physical properties that allows quite a wide range of applications. One example is the free recovery up to the 8% in strain, which is something quite outstanding for an alloy, a metallic alloy. And it has a lot of other important and useful properties, such as high corrosion resistance, biocompatibility, and workability, in order to obtain different semi-finished products for a lot of different applications, and so on. The second step in the Sma design is the thermomechanical condition, because the main objective is to functionalize the material in order to obtain the desired features, the features of transformation temperature, in order to work at a specific temperature required by the application, the required stresses and strokes, and so on. The thermomechanical state is of a material, and the specific of shape memory alloys is given by both the production and the processing of the material. The first step is the production, which is divided into two main families. We can produce alloys and shape memory alloys, in particular by casting, traditional casting, or also powder metallurgy. In powder metallurgy, we have both traditional sintering procedures, and also additive manufacturing is nowadays highly studied and a good perspective for the future of alloy production and shape memory alloys production. Then, once you have the material, usually it has a surface finishing which is not good for applications, and also its properties are not the desired properties, because there is a post-production processing that is required, and in particular hot working or cold working, depending on the kind of alloy. Thermal treatments are fundamental, and also other techniques such as joining or surface treatment. Among thermal treatments, we can adopt some solutions such as solubilization, annealing, or aging, which are thermal treatments between 300 degrees and 800 degrees for different times, depending on the desired properties that we want to obtain. Indeed, the aim of this processing, and in particular of thermal treatments, is to have a shape setting of the component of the material, because if we heat up the material, the shape memory alloy constrained in a mold, we can obtain the desired shape of this component. And the other important thing about the thermal treatments is that they allow to obtain the desired functional properties. As I said before, we can obtain a lot of different semi-finished products with all these processing techniques, and among them, for nickel titanium in particular, we can obtain thin wires, thin films, tubes, ribbons, plates, and important for the Sma project, springs, meshes, and finally we can also apply the laser cut to nickel titanium components, as is used for the stands, for examples. And finally, the fourth step, very important, is the characterization. So when we have produced, processed, and given the desired shape to the Sma element, it's important to characterize it in order to know if the final properties, functional properties of the material are the one that we wanted to achieve. Among principal characterization, we have the calorimetry, electrical resistance, mechanical tests, and microscopy in order to check the evolution of the transformation and of the transformation temperatures. We want also to observe the microstructure in order to know if there is the desired homogeneity in the material, if there are defects, and so on. The main limitations in the design with shape memory alloys are the high heat capacity together with the high density of these alloys, which give the problem of the slow cooling phase when we are dealing with, for example, actuators, because actuators need to be continuously activated, and the transition always have to be activated and then done again. And so if this shape memory alloys has this high heat capacity and high density, the cooling phase is quite slow, and this is not a very good point for the applications. And so the solution is to optimize the design of the component, and to also maybe to project a refrigeration system to help the material for the cooling. The second limitation is the low energetic efficiency that we can face when the material is put inside a real device. And so again, we have to optimize the design, maybe by the optimization of the state of the stresses that the material has to face. The third problem when designing with Sma is the durability, since the material can be degraded due to overheating and excessive deformation that can occur during the use of the material, of the component. And so it's important to choose and control carefully the operating conditions. However, there are also a lot of advantages when designing with Sma. The first one, the most important, is the reliability, since the physical transition in shape memory alloys always occur when the shape memory alloy material is stimulated, since the functional properties of the Sma are intrinsic properties, and so the transition will always occur. The second point is the simplicity and the compactness of these systems, since the operating concept of the Sma is quite easy and essential. The main example is the spring and counter-spring actuator. And finally, also the possibility to have a wide range of movements and stresses that is not so, that is a good point for a metallic alloy. And it is possible also to develop micro and mini actuators in this sense. Now to have an overview about the sectors for the application of shape memory alloys. We have the development of mechanical components in the automotive and the aerospace field. Then we have the robotics, and maybe the most field sector is the biomedical, which is the field in which there are some industrial and developed solutions, such as the orthodontic wires made in Nitinol, or also the stents. Considering the main application of the shape memory effect, we have examples of, first of all, of the free recovery of the shape memory alloys in applications such as gadgets or furniture solutions, but also two-way shape memory effect sensors, in which the active part of the sensor is a simple wire that deforms freely and goes to actuate this device. And another example is a deployment system for, in this case, a thermal panel. On the other hand, we have also a shape memory effect application in constrained recovery. We have examples in the biomedical field, in orthopedic devices, and also ring-like wire for suturing. But there are plenty of applications such as joints and active connections or self-healing structures, and rock breaker and marble cutting, which are all devices which are quite simple in their use and in their working concept, but they are quite good. And other application for the shape memory effects are the actuators, because shape memory alloys have the advantage that allow to obtain, for example, both linear and rotational mini actuators with very compact geometries. Also, again, sensors, and these two are two systems that are industrially developed for the aerospace field, and they are the frangible and pin puller systems. Here we have another example of actuator, the amagnetic actuator. And again, also this simple functioning allows to develop a lot of solutions dealing with valves. In this example, a thermostatic valve and a concealed Springer valve. And this also is an interesting application, which because it is both a sensor and an actuator. Again, for the fire smoke systems. Another interesting application for the shape memory effect is the morphing, which allows to design variable geometries. Here we have an example, and for example, this is the smart wing in the aerospace field. And another point is that you can integrate the shape memory alloy films or wires into matrices and also complex geometries in order maybe to integrate these components into more complex devices. Considering instead the superelasticity and the superelastic applications, the main fields is the biomedical field with the stents, which exploit the superelasticity during the phase of the release of the stent inside the body. And other examples in the biomedical field is the rehabilitation field with the orthesis that work with these shape set wires in the junction of the orthesis. Here another example about occlusion system for the atrial septal defect. And other important application of the superelasticity are a pseudoelastic joint for big mirrors in telescopes, and other kind of supports for, in this case, optical devices. Other application regards the elastocaloric application, which exploits the ability of the shape memory alloy material to release heat and absorb heat when stress is applied adiabatically on the Sma material. And there are some solutions that have been developed both on the macro and the micro scale, with the material under the form of wires or sheets or ribbons and so on, which is periodically deformed, and the heat that is generated is sink into maybe a refrigeration system. In fact, these elastocaloric applications are now studied, and they regard principally the solid state refrigeration, as Elena said before. Then, important applications which are related both to the pseudoelastic properties and the martensitic properties of the Sma is the damping. And damping of different kind of vibrations both diffuse vibration that can affect vehicles, for example, aeroplanes or trains or helicopters, and so they can be integrated, the Sma can be integrated in structural components in vehicles. But we have also the high-intensity vibrations that are typical of the seismic waves, and so some Sma solutions have been developed for seismic structures and anti-seismic systems. And also shock absorber are an important developed application for the damping. And in the light of in the field of this damping, we have developed some demonstrators also within the framework of the Sma project, and you can find also down here the demonstrators, which are some dampers, a cladding panel for the damping of diffuse vibrations, and a shock absorber for low energy impacts. And the dampers and the cladding panel have been developed through the use of plain woven mesh made up by thin wires of nickel titanium and steel, produced by BOP, which is a Swiss company. And in these two cases, the mesh was shaped in different ways in order to be the active element of these kind of demonstrators. Considering the dampers, we saw that we characterized them, and they proved to have a good damping behavior over a large number of cycles. And here we reported the internal friction parameter, which is the parameter related to the damping ability of a material. And considering the cladding panel, we developed this solution, which showed to have a good damping for the diffuse vibration at low intensity. And interestingly, it has it showed a high damping at specific frequencies, both at low temperatures and high temperatures. And this could be considered as resonance frequencies, so it can be studied for some in-temperature applications. And finally, we developed also a shock absorber for low energy impacts, so impacts at a small scale. And in this case, we used as active element nickel titanium superelastic ribbons. And the main feature of this shock absorber is to recover the original shape after the impact upon heating. And the possible application of all these demonstrators, which are sort of pre-prototypes, are the integration in anti-vibration supports in joints. Maybe they can work as adaptive seals, and also in the case of the panel for anti-vibration cladding. The free mesh could be used around the tubes, shafts, or pistons. And in general, all these semi-finished product, the mesh, could be integrated or used as an actuator. Thank you for your attention, and I'm available for questions. And you can see the demonstrators that I show you down here later, maybe.
I might have a question to your last slide. How can you tailor the frequency at which you have high damping? Is that a material property, or do you tailor that with the geometry of the cladding panel?
Yes, this specific property of specific high damping for specific frequencies is a combination of the property of the material and the geometry. So if you can tailor these frequencies by producing panels or sheets and so on by different dimensions, maybe a different dimension of the shape of the wave, and you can tune in this way this property, yes, depending on the desired application and so on.
Other questions? If not, then you'll have the opportunity, of course, later on. Thank you. Then we'll move to the next speaker, which I think is Giuseppe, right?
Hello everybody, my name is Giuseppe De Ceglia and I will talk for Tecno Springs Italia and also for TSS Innovation Project, and my colleague is over there. Well, today I will talk about some industrial application, practical application from our productions. I will first introduce the two companies and then have a look on how the SMA products are produced from a practical point of view, and then I will show you some example actuators that we produce and some result from the Sma project. Well, Tecno Springs Italia is an Italian company. We are located in Besnate, near the Malpensa airport. And we are 40 employees today, and basically we produce springs. We produce metallic elements, elastic elements in any kind of metal, basically. And for any application, we have a very broad spectrum of clients, from home appliance to automotive, oil and gas, very, very broad spectrum of customers. We also have some quality system certification, the ISO 9001, 90100 for aerospace applications, as well for the quality system for medical and biomedical products. And also we are NADCAP for the heat treatment, mainly for aerospace applications. Next, TSS Innovation Project is the other company. It was born as a spin-off of Tecno Springs Italia, and it's located in Roveredo, here in the Grisons. Today it has 5 employees, and it is a spin-off of Tecno Springs, so the production are almost the same, more focused for Swiss and German market, and for medical, automotive, and watchmaking applications. So here you see our products. We produce with any kind of material, metallic material, from carbon steel to stainless steel to special steels, so spring flex, nanoflex are some kind of nanotechnology-based steels. Also, we work with titanium alloys or high-temperature nickel-based alloys like Inconel, and sometimes with some esoteric for springs material like copper or aluminum for very special applications. Our capability of production is starts from 0.06 millimeter of wire diameter up to 14 millimeter for standard production and up to 20 millimeters of wire dimensions for standard compression springs. We also produce extension springs as well, torsion or complex shape like rings or bent wire, any complex shape. Like on the right side, you see also spirals, constant load springs, or wave springs. Well, all of these springs are made of conventional material. We are all today here for shape memory alloys. So what we can produce with shape memory alloys starts from nickel titanium, basically. There are, my colleagues before told you that there are a lot of shape memory alloys, but from a commercial point of view, nickel titanium is the most available in the market. So there are some ternary alloy like nickel titanium copper that can be used, or some copper base for high temperature, but mainly we produce actuators or products with nickel titanium. We do not produce the alloy, so we buy the material in the form of wire, strip, tubes, and from the raw material we produce what we need. So I will show you what is the overall process in order for you to have an idea what is a SMA product. So starting from the raw material, the very first step is sort of mechanical deformation. We have a shaping of the material. It can be done by a machine, or it can be manually in case. After the deformation, we have the so-called shape setting. So it is a thermal mechanical process in order to give the final shape to the component, and also to give the final thermal mechanical characterization of the product. This is a very critical phase in the production. Afterwards, there can be some additional operation, for example, grinding for a spring, or surface finishing, if you want to have some kind of nice surface finishing, or if you want to remove the oxide for biomedical application, it depends. So all these processes are our know-how in order to get the final product. So after this, you may ask, okay, why shall I use SMA design? The production process is quite complex, so the material is not, is quite expensive. So you have the cost of material. There are other technologies that are already used and they work. And in order to have a new device based on shape memory alloys, you have to spend time and money. On the other hand, you have you can reduce the complexity of a system. You can reduce the weight of a system. You can get something that is new and functional. So the answer to the question is, it depends. It depends on the trade-off between all these aspects. So going to the actuation modes, both Elena and Francesca already told you what are the possibility to use the shape memory alloys. I will just remind you briefly the three possibility. Sensing the actuating systems, the shape memory alloy responds to a change of temperature and responds with a change in macroscopical shape. So you can exploit this in order to produce a work output. This allows you to make a sort of actuator that is both sensor and actuator at the same time. This is really interesting in order to produce some completely passive actuator. The only limitation for this kind of application is that usually the actuation is just one way. So you need something to recover the original, the starting position. Usually there is a coupling of a shape memory alloy and a bias traditional spring made of steel, for example. Then you can use the actuation with an electrical drive. In this way you can heat it up, the temperature, either by direct Joule effect, so direct current, or with an indirect heating, for example, with a heater. And in this case, also you can have a very high work output per volume, so you can have a very light and compact actuator, even though there is the drawback of cooling the device. So it's really easy to heat a component, but it's difficult to keep the heat when you need to cool it down. The other drawback, I would say, is the possible low efficiency. So also in this case, it depends on the application, strictly on the application. The other possible application is the superelastic. I will show you yet again the typical flag shape of the shape memory alloy, and you can exploit very large deformation for metallic material. You can also, in the same way, you can exploit the constant force of the force plateau that you have at the high deformation. For example, this is widely used in medical field for example, for the stents, or for arch wires, or staples for bone fixation. Then there is the last topic, that is damping. And I will show you some demonstrator that we made with shape memory alloys for the project. So these are the 5 fields in which we are active, mainly for shape memory alloys. So we produce actuators for fire system, for ventilations, automotive, medical, and aerospace. I will show you some products from our companies for all of these fields. Starting from the fire systems, this is the very first product of our company in the shape memory alloys field, and it is a Naval Sprinkler. So a sprinkler, when a fire is coming, the traditional sprinkler is made of mercury bulb that breaks with the heat and open the water spray. We replace it, basically we replace the mercury bulb with a shape memory alloy spring that at a certain temperature exert about 7 Newton of force in order to open the water spray. The advantage of this system is that you do not have any mercury bulb that can break very easily, and so it's quite easier to transport, to mount, and also in principle it would be also reusable. It's not done, but in principle it could be. Another example from our production is the so-called fire dampers. So they are safe system in case of fire that based on a shape memory alloy spring. Upon heating, there is a shape recovery with the spring, and a system, a mechanism will shut or open. It depends on the system, the airflow. I will show you later on. I have a demonstrator of of this one. Other application could be ventilation. This is a very intelligent way to use the shape memory alloys, in my opinion, because you can get a completely passive actuator that feels the ambient temperature to do something. In this case, we have a sort of blade change, intelligent blade. So the hot air will be directly blown to the bottom of the room, while if you are blowing cold air, it is addressed to the side of the room. This is done completely automatically by the shape memory alloy spring, of course. Here you have an example in the automotive field. It is a thermostatic valve, basically. The system is made of a shape memory alloy spring and a bias spring. The aim of this valve is to prevent the windscreen water to freeze in winter. So a secondary circuit of the cooling system of the car is either blocked, stopped, or flow through the windscreen water in order to how can I say, to hit the water and not to make ice in the container. Other applications are in the medical field. Here we are active mainly for super elastic devices. Here you see an example of marker for tumoral applications. So the device is a sort of ring. The diameter of this wire is 0.4 millimeter and has a circular shape, but you can put it into a needle, so you can straight it completely, and then after you push out from the needle, it recovers the original circular shape in order to be fixed on the tissue in the body. Here there are some other medical applications in dentistry. These rings are for dentistry applications. The one on the right side are part of surgical instruments for example, for operation at the shoulder, and the other one for the spinal applications. This spring, okay, is not really clear, but is a endoscopic spiral. The wire diameter is 0.6 millimeter and the spring diameter is 0.856 millimeter. So it's really, really small. And this is super elastic. This is another application that is a cranial fixation device in order to fixate cranial prostheses in ceramic material. Well, I don't say anything else about that. Then we can go to the some space application. These are more projects than applications for our purposes. The shape memory alloys are used basically mainly for actuators for space. In the field of all-down release mechanism, you need to know what is all-down release mechanism. It's an actuator needed in order to hold down some appendages in satellites during the launch of the satellite. And once in orbit, the satellite needs to be, all these appendages need to be released on command. So the all-down release mechanism is what is the actuator that allow this deployment of appendages. The advantages of shape memory alloys in this field is that they are low shock compared, for example, to pyrotechnical actuators. They are resettable and reusable, and so they are testable before launch. This is not possible with other actuators, for example. And they are not so complex. So also they are quite lightweight, so they can be used easily in space application. Here you see what is the so-called Shrek Device. That is an all-time release mechanism based on nickel titanium torsion bar. This is a device. It started as a project, and today it is a device. It's going to be mounted on the next Platinum mission, Platinum satellite. Then we had another project we concluded last year, this GSTP project founded by ESA in order to develop a high temperature pin puller. The great advantage of this device should be the wider operational temperature compared to commercial available shape memory like alloy pin pullers on the market now. And then on the basis of the high temperature pin puller, we developed a smaller pin puller in order to be used on CubeSats to open the CubeSats and to be released in the space. I have also a demonstrator for this. Later on I can show you how it works. Then something about the Sma project and the damping properties. Well, we are companies, so our idea was to start from a commercial need and to apply the technology, the damping technology of shape memory alloys in commercial problem. So we had some requirements from the naval field and from aerospace and helicopter in a particular field. So we started from commercial devices and we tried to develop something new. I will show you both of this demonstrator, and just for you to have an idea. So this was the idea of this small actuator is to integrate a sort of shock absorber in the floor of helicopters that can absorb shocks in case of impact. It is based on a shape memory alloy wave spring. That is a technology quite new. It's not possible to find it in the market. It's not easy. So we developed this technology in order to have a shock absorber made of this new shape, let's say. Well, these are some data. The data are really nice, but I think it's easier to show you what is really the possibility of this device. So I'll show you this small video. On the left side, you see the springs in hot state. On the right side, the springs in the cold state. So you see that when the material is in martensite, it can absorb a lot of energy. So there is a back bounce, a really small back bounce compared to the other condition. So the idea is to use the material and to choose the transition temperature in order to have a shock absorber, of course, at room temperature. This is a very promising way to develop. We are still working on it. The other application comes from a naval application. So on the left side, you see some commercial product. They are mainly used for shock absorber and vibration dampers also. For example, on the basis of racks or instruments in the naval field. They are made of stainless steel rods. Our idea was to replace the steel rods with nickel titanium wires. The results are quite promising. Also in this case, you see graph. Okay, it's not really exciting, but I can show you what is the possibility of this. If the video starts, of course, yes. What is the real innovation and possibility of this material? So after the shock completely deform the device, upon heating, the shape can be completely recovered. In this case, it is in a thermal chamber, but you can make just by heater. And this is a unique property for this device. So we are trying to improve and develop this idea. Also, as a vibration damper, there is some possible improving properties. We are still working on it. On the right side, you see the commercial device. On the left side, you see the shape alloy based. Well, this is just prototypes, and we are still working on it, but yeah, it's promising, I would say. So, here's everything for me. If you have any question, we are available for anything. Please.
Do you fabricate this shape memory wire yourself? You buy it?
No, we buy the wire. We buy the wire. There are several suppliers. But yeah.
I was wondering for the sprinkler wires, when you produce these wires or these springs, what is the range of or the accuracy of at which temperature each and every spring would actually open the sprinkler? Are we talking about when you produce thousands of them, plus minus half a degree centigrade, or 5, or what's the range?
Well, that are the specifics. So, in order to be activated, you need 7 newtons plus minus 1 at 57 degrees.
Right.
So this is the range. It depends on the application. It really depends on the application. So, yeah, you need to consider also the thermal hysteresis that you have on the springs. Well, in this case, it's not so important because you have a thermal hysteresis when you cool it down. But in case of fire system, you just have a heating, so you do not have a hysteresis. There are several factors that you need to consider before, well, in the design and in the the production process.
Mm-hmm. And I guess you also have to take into account the batch of material that you receive, and can you test that? If you receive a new batch that has a slightly different alloy structure.
But well, you're right. We receive, in case, for example, for the automotive field, we have thousands of springs produced in 100,000 in a year. And of course, you have different batches of material. We buy the material always with the same specifics, the same standards. We need to test it before, and we can adjust a little bit the process in order to get the final spring that we need. And we have the capability to test both the material before and the springs later on. please.
So if I understood, you purchase the material as
Yes.
a raw material, and for adjusting the temperature, etc., you have the thermomechanical treatment that you do by yourself, except that the deformation, etc., you have the special thermomechanical treatment adapted for adjusting the temperature, etc. Isn't it?
Not really. I mean, we purchased the material and all the process that I showed you, these process here, maybe this one. So we buy the material and all this process here is done by internally. So from this coiling, we are spring producers, so this is our core business, making springs. And then we developed also the shape setting and the training of the material in our company. You're welcome.
All right. From the previous talk, I remember this force-free or stress-free deformation. I think it was mainly for design purposes. I remember this flower opening up and closing. Are there any more application of stress-free SMA?
We had some in design, so no stress-free application. I don't remember any application for this. Maybe jewelry.
What would be possible also
It
to
would
use?
be possible to have something else.
Like to use this fire sprinkler or this water sprinkler being closed automatically after the fire is extinguished, for example. Would that be possible?
Well, usually the shape memory alloy, the nickel titanium is it works well in one way. In order to have a two-way actuator,
You need the stress.
yes, it is not really, it is possible to have a two-way actuator standalone, so just the shape memory alloy itself, but it's not really efficient. So,
In which way is it not efficient? The reverse way is taking
Both
long or taking long time?
it just changes the shape. It doesn't make anything else. It's just changing the shape. So if you need just a bit of force, it's not working very well. So usually in application you need some work output. And in order to have work output, the best way is to have one-way sensor and then a bias force in order to get back in the original position. It's better to have this kind of application. But of course, you can have two ways as well, in case.
What's the lifetime of such actuator? How many cycles
For the self-actuation or in general?
in general? For 1 million
It de-
cycles or?
Well, this is strictly dependent on the design of the actuator. So it depends on how you design the actuator. So if you want to have, for example, a very large strain, you cannot have a large number of cycles. Vice versa, if you have small strains, you can increase the cycles. There are a lot of studies for cycling. Usually they are mainly on super elastic devices, mainly for medical applications. There is some literature also for actuators, but it's something that companies usually do not say they don't want to disclose too much about this. Yeah. Anyway, for the automotive application, this is a quite critical issue.
Limiting.
But in our product, we do not have this problem. We had severe tests on the springs, on the valve, and we passed all the tests for the I would say, the car lifetime. So, yeah.
For example, in the market, there is the possibility to buy wire stabilized for deformation of about 4 or 5%, developing 250 megapascal for 250,000 cycles. There is the possibility also to buy material prepared and focused for this cycling performance. But about 200,000 cycle is a medium aim reached by different kind of wire, ribbon, and so on. But is very strictly related to the application, to the design, to the strain considered. For pseudoelastic and very low strain, we can consider also gigacycle, because the aortic, the heart application, now the valve for heart, now there is a valve in nickel titanium. And then for pseudoelastic application, the gigacycle are reached.
You have to consider also that most of these studies are done on a specific application. So as long as you change one parameter, it's not valid anymore, or it might not be valid anymore. And all this, Elena was talking about wires. If you talk about springs, everything changes. So, yeah. Oh, you have a question, right?
I had a question about the two-way shape memory alloy. No. Never mind. But one question, what do you mean by shape setting? You deform the material to the final shape or pre-final, and then you do thermomechanical treatment on that?
The second option is more correct. So we pre-shape the material, and then we have the final shape setting. That, of course, is not completely different. The preset is not completely different from the final shape, but it is not exactly the final shape. And also with this shape setting is included the thermomechanical characterization, I would say. So with shape setting is a broad, you change a broad part of the parameters. For example, the activation temperature, the shape, the lifetime of the device. All this parameter depends on the shape setting.
In the example that you showed of the fire extinguisher,
yes,
this design seems such a much smarter way than having a mercury bulb for doing that job. Why isn't this used everywhere? Is it just the price, the disadvantage? Or are there other...
This is the answer.
The price? Only that. Otherwise, the performance is...
The price is the key word for example, for the automotive valve.
Yeah.
In that case, it was not cheaper than the already used valve, that is a workspace valve. But the advantages were the weight, the dimensions, because the valve is smaller, so you can insert in more complex shaped containers. And even if the cost was a bit larger than the works valve, the trade-off was, okay, let's do that. So yeah, I think the price is a very important part of this.
And just to have an idea, if in this application for the fire extinguisher, are we talking about double the price for the final device, or?
Yes, more or less.
Okay. Yeah.
Anyway, the wire is not so expensive. I mean, if you have 1 gram of spring, you can generate 10 newtons, for example. and 1 kilo of nickel titanium costs $250. So it's something you can afford in many applications. It depends how much you want to spend, always.
It depends also on the quantity of springs that you want. Because this is, for example, the price if you buy
A lot of
200 kilos of material. If you buy 1 kilo, maybe you pay 1,000 euro per kilo. So everything is always the same thing. It depends on what you need and what you want to pay. That's it.
Right, thanks. Then we get to the last presentation.
So my name is Václav Pejchal, and together with my colleague David Novo, we are going to present from Cscm side the perspectives and shape memory alloys in mechanical systems from design, material, and process perspectives. So I start the first part from the additive manufacturing component reliability sector, and then David will continue from the precision mechanism systems, where they used the shape memory alloys in some practical applications as well. So to just start a little bit at the beginning, I will mention additive manufacturing at Cscm. We are two sectors that are collaborating together. A sector that I'm coming from, we are around 12 people that we are working on manufacturing, quality assurance, characterization, development of additive manufacturing process. And on the other side, we have our colleagues from system engineering who do the design and work a lot on flexible mechanism compliant structures for space applications. And yeah, here's David and here's me. So to start with, I don't go too big the details. It was already explained what shape memorials are and how they work. I will just basically repeat that we take the advantage of the solid state phase transformation between martensite and austenite phase, and particularly the fact that martensite actually exists in two different forms. One that we call the self-accommodating martensite. It's the one that we obtain when we, for example, do laser powder bed fusion, and the material is at a high temperature in austenite. When it cools down, it transforms in martensite, and the material is lazy, it doesn't want to deform. It forms the self-accommodating martensite that is full of twins. And then when we deform this martensite, it's soft, and it's actually not the plastic deformation that we observed is mostly the detwinning of this self-accommodating martensite into the single variant martensite, detwinned martensite. And then when we heat it up, the single variant martensite returns back into the austenite, the high temperature phase, and then when we cool it back down, it goes back to the self-accommodating martensite. We can actually train the material so that it doesn't go from the austenite back to self-accommodated single variant, the self-accommodated martensite back to the single variant martensite, in order to obtain the, what we call two-way shape memory effect. And that's one of the topic of my talk. But both are useful, and it was already mentioned that there are devices that mostly use the one-way shape memory effect. And I will have also one slide where there are some basic examples how does it work. It was already mentioned that shape memory alloys like nitinol, nickel titanium can offer a high actuation stress, high actuation strain, up to 6 or even 8%, depends if we talk about one-way or two-way shape memory effect. And It also has a high energy density, which was already mentioned, that we can make compact devices. And what is important when we talk about nickel titanium, but also other types of shape memory alloys, is that they usually have a very strong dependence of their transformation temperature based on the composition. So you can see that with as low as 1% of atomic percent of nickel content, we can have quite a high difference in transformation temperature. So this is something that needs to be correctly chosen and characterized and also qualified for the use. And especially important it's in laser powder bed fusion, where we actually produce the material out of powder. So why additive manufacturing? So you've seen already that there is a lot of devices that exist. Of course, they can be complex, but there is a problem with especially machining nitinol. So nickel titanium is not easy to machine. We learned it ourselves when we just tried to make a build plate. So when you use laser powder bed fusion, you need a build plate on which you have to start with the material to build material on top of it. And just making a nickel titanium build plate, it's a challenge of itself. And most of the complex geometries are today using wires and braiding or knitting wires together. With additive manufacturing, we can have larger freedom in design space, and we can really try to untap the potential that has been hindered so far due to geometry restrictions. And at Cscm, we provide basically all necessary skills that are for this kind of job. We can work on design, process development, but the manufacturing, characterization, and quality assurance. And just to have an idea because complexity is a very relative thing. So when I talk about complexity, this is the complexity that we achieve with laser powder bed fusion today. This is not nitinol, this is 1740 stainless steel. But this is a complexity where we can go with laser powder bed fusion today. So we can talk about various structures for pointing mechanisms, but also one of the topics that we worked lately was where the pointing mechanisms with lattice structure blades, etc. So just when I talk about complexity, it's this order of complexity that is achievable today. So laser powder bed fusion process at Cscm, we handle what we call end-to-end development. So we really start with design and topology optimization, for example. Then we have capabilities to characterize and qualify the powder and how it can impact on the manufacturing. We work on the defect and microstructure investigation, and also post-processing. When we talk about laser powder fusion, it usually the powder is the feedstock, and we use laser to fuse the material locally in order to fuse it in a layer by layer process. At Cscm, we have TruePrint 1000 machine, and in 2022 we will have a new EOS machine capable to build larger structures up to 250 millimeters in one size, in the long dimension. So when this process is applied to laser powder bed fusion of nitinol, what does it mean? So as I already mentioned, the feedstock qualification, we need to have a feedstock that has the right chemical composition, transformation temperature, the powder that has the right size and flowability. The process development, we need to be assured that the laser powder bed fusion gives us the right density, the mechanical properties. Again, the composition can change during the process. We melt the material. It's at high temperature. We need to control the atmosphere. We have to be sure that what we get out of it, again, has the right transformation temperature and mechanical properties. Then post-processing, we need to further functionalize the material so that we can have obtained one-way or two-way shape memory effect. So we can do post-processing, do the training for two-way shape memory effect, and, for example, integration of actuation by heating elements or integration of wires for joule heating, etc. And finally, we need to perform testing, qualification for performance and validation of the effect. So this all can be done at Cscm, and here I will show you one case study. So we have a project together with company Almatec that is based in Lausanne, in the western part of Switzerland, and we are working on self-actuated, flexible space mechanisms. They are not anymore flexible, so the initial design and idea is what we call a large angle flexible pivot. It's a pivot that is used in space applications for pointing mechanisms, and usually you need a motor so that this can move. It's using the flexibility or elastic properties of steel or other materials. Here the idea is to so the applications of large angle flexible pivots could be in flip mirrors, high accuracy pointing mechanism, or louver windows. You will see one of application in louver windows using shared memory alloys will be presented by David. And so we can actually, we have to use the motor. There are some connections, there is a backlash in the motor and micro vibrations. So all this can be tried to solve by shared memory activation, where we don't have micro vibrations, there is less of assembly needed, and also the control electronics can be simplified. And when we combine it with 3D printing technologies of Nitinol, we have increased freedom in design, we can do monolithic fabrication, and we can control the transformation temperature. And altogether, this is a topic of 4D printing. The fourth dimension is time, and we are working on the next generation smart flexible mechanisms or pivots. And in this case, we wanted to demonstrate the mechanism at room temperature as the reference. So this is important because then you have to choose the right transformation temperature. But basically, if depending what's your reference temperature, then your transformation temperatures should be taken into account. So first, we need to have the right feedstock material. So in laser powder bed fusion process, we work with microscopic powder material. So we have qualified the powder based on its morphology. It needs to be spheroidal, so it has a good flowability. The right phase composition, so at room temperature, we want it to be having martensite. The particle size distribution needs to be right so that it's printable. If it's too big or too small, it wouldn't work for laser powder bed fusion. The right flowability, in this case, it had an excellent flowability manifested by the Hausner ratio that is very low. Transformation temperature, in this case, we had austenite start temperature 60 degrees and martensite finish 25 degrees, which is the right transformation temperature to demonstrate shared memory effect at room temperature as the reference. And the chemical composition was also important to have a low amount of impurities and the right amount of nickel so that it has the transformation temperature as shown. So then we did the design of experiment study for parameters optimization. We usually talk about several parameters that needs to be optimized in laser powder bed fusion process. It's usually laser speed, laser power, the hatching distance, so the distance between each laser track. Then you have also a contour that is just basically the contour of the part itself, the layer thickness, and etc. So we have optimized the parameters at the beginning. For example, during the process, we do microstructural analysis. We've seen that in some promising recipes, we've seen that we had still some non-optimal hatch distance. That's usually seen by observing a lack of fusion defects that are aligned at certain points. And finally, we achieved parts with relative density in as-built samples higher than 99.85%. Of course, that this could be even further improved, for example, using hot isostatic pressing, but it was good enough for our application. Then we did material qualification of the optimal parameters for laser powder bed fusion. We did differential scanning calorimetry in order to measure the transformation temperatures. So the martensit finish was 35 degrees and austenite start 70 degrees. You can see that it's already slightly higher. This is usually the fact because there is a different rate of, let's say, evaporation of nickel and titanium. So actually by changing if you have a very high power, you can actually change the shift towards higher transformation temperatures when you have a material that starts at lower temperatures. And we did also phase analysis. So at room temperature, we have more than 90% of martensite in the as-built nickel titanium parts. So then we did the verification and validation of one-way shape memory effect and characterization. So here is one stress strain curve. This shows the ultimate tensile strength near 450 megapascal and maximum applied strain at the moment of failure near 6%. With estimated maximum applicable permanent plastic strain for shape memory recovery up to 5%. This has been measured using three-point bending tests, where we observed up to almost 4% of one-way shape memory effect for strain recovery. I will make a small parenthesis here because we have demonstrated one-way shape memory effect in already as-built samples, and as it was mentioned, this is already useful to use in actuators. So just a small parenthesis how we can use the one-way shape memory effect. So we need something to apply strain in our part. So with the heating, we always obtain the reverse effect, but we need to apply strain. And this strain can be applied by mostly three different applications or three different setups for actuators. So one is to use actually counterweight, very simple, but probably not easy to implement in a real actuator. Then we've seen already several applications using bias actuators, so biased spring, for example, so that's very clever way. But what's even more interesting is to use actually another shape memory element and use it in so-called antagonistic SMA actuators. So you are hitting one and that one is acting upon the other that is in cold shape and the other way around. So that's so-called antagonist SMA, antagonist-agonist SMA type of element. So these are three basic types of actuators based on one-way shape memory effect. We went further and we really wanted to observe also and to validate the possibility of having two-way shape memory effect. And in this case, we want to obtain basically single variant martensite upon cooling from high temperature phase, and the process to obtain this is called training. There are several ways how to train nitinol or shape memory alloys. In this case, we used so-called constraint cycling of deformed martensite. So in this case, you set the shape to so you have the beginning the default shape that is upon laser powder bed fusion. Then you deform it at cold state into a different shape, and you heat above AF and below a martensit finish. We did this 100 times on a simple flexure blade, and we have observed two-way shape memory effect. So in the hot state at 130 degrees, it was having a higher angle, and in cold state at 20 degrees, it was having a different angle, and we were measuring. There was roughly 30 degrees of difference between hot and cold state in 0.6 millimeter thick blade. There is a slight shift or creep of these angles. This is something that is observed also in conventional shape memory alloys. It's something that is related to the two-way shape memory effect, that it's difficult to obtain perfect stability, and either it can be considered in the design, or there are some very few tricks that can be worked with. And then we went to the actual demonstrator manufacturing. So we have optimized the design for the strains for two-way shared memory effect, and we have demonstrated the manufacturing of full demo using laser powder bed fusion. We brought it today with us as a demonstrator, and we had to optimize the build orientation, support structures, and their removal. In future, we will use off-the-shelf flexible heaters to heat the blades. So here only the blades are functional, that's supposed to move. So we don't need to heat absolutely the whole structure, but only the blades, and especially where the strains are at its maximum. So it's very localized strain that is applied and needs to be recovered. And the training and testing campaign is scheduled for the beginning of 2022. So in conclusions and outlook, so one-way shape memory and two-way shape memory effect were demonstrated in S-built laser powder bed fusion nickel titanium parts with more than 99.8% density. One-way shape memory recovery was near 4%, and two-way shape memory effect was also demonstrated, and detailed characterization is ongoing. The phase transformation temperatures were optimized for shape memory effect demonstration at room temperature, with austenite start and martensite finish temperatures above 20 degrees. And of course, also super elastic behavior is possible with optimized powder feedstock. So if we have a different either reference temperature, we can use also the same, or a powder feedstock with different content of nickel can be used for phase transformation below martensite start below 20 degrees. And we can use this for flexible, again, flexible mechanisms. So where we have large angle flexible pivot, we can imagine even larger angles using a similar design, or for damping structures is also very interesting, as it was already mentioned. There are some challenges ahead. There is one peculiarity of shape memory alloys in the training. So during the training, actually, so this is a stress or basically strain as a function of temperature. So during first cycle, there is a certain maximum strain that you achieve, but during the training, this strain increases, and this is very important to take this into account in designing, for example, two-way shape memory actuation. It needs to be taken into the design at the very early stage, and also it brings certain aspects in designing of future actuators. So it's important to master the training procedures, it's absolutely necessary, and its implementation in design. Also, it's important to have a sufficient local heating. Nitinol is relatively good conductor, so in certain sizes, it's not efficient anymore to use joule heating. And for example, in-house in Cscm, we have development of our own sensors using inkjet printing, but it can be used also for printing locally using inkjet printing flexible heaters that we can apply to locally heat the structure only where we need it. And finally, the stability of shape memory effect is also very important. There are actions that can be taken on material or on design side. So thank you for your attention. This is the first part of our common talk, but maybe if you have some questions, you can ask me, and then David will continue with the other part.
Just a question about the powder. Do you produce by yourself, or do you
No,
buy?
We buy powder from commercial, industrial, available producers.
You go to previous slide, please. No, is it any reason that the lamella doesn't pass through the center?
Yes, so that's the optimization of the strain actually. So if the lamella doesn't pass through the center, or so basically, yeah, that's a good eye, Masoud. So basically this lamella, its axis is not in the center of the axis of rotation here. So actually when it would pass through the center, the stress distribution would be completely different actually. Not only in magnitude, but also in a mode over here.
Thank you.
In certain configurations, one can actually achieve almost uniform distribution of stress in the element, whereas we wanted to really localize the strains near the hub so that we don't need to heat the whole blade.
Do you see any anisotropy in printed structures, so that like mechanical properties depend on how your structure was built, and you see influences from the layers or something like that?
So in laser powder bed fusion and as-built material, this is absolutely possible. We haven't done characterization at this stage for that, but what we have done is that after the printing, it's possible to do solution annealing, and this usually resets these kind of effects. So when the anisotropy is of issue, a solution annealing is one of the ways to reset the microstructure, so it's not anisotropic.
When you do this 3D printing, defects in the material might be a topic to look at. I think you had also a slide in there. How does defect actually influence the mechanism of the whole structure?
That's an excellent question. So there are various defects that can be produced during the LPBF. So at this stage, the most important was to not have the most defects that would decrease the strength of the material. So we wouldn't be able to go to high enough strains to have the sufficient strain recovery or one-way shape memory effect or two-way shape memory effect. This is a topic of itself to go into the efficiency of the shape memory effect with certain types of defects like microporosity, for example. Then, of course, there are precipitates that we can form during post-processing that affect the performance, but also the shape recovery. So it's a topic of itself, and at this stage we didn't go to big details of what each type of defect could have an effect on that, and that's a beautiful topic to work on from the material science side.
Thank you.
Thank you. Okay, so it's my turn. Good afternoon or good evening, everybody. My name is David Novo. As Václav told you, we both work at Cscm in Neuchâtel. And now I will present you maybe a different presentation than the other one, because here I'm going to explain an industrial project where shape memory alloys was used. And the idea of this presentation is to tell you our experience or our feeling with this technology. So the project name is Cooler, and it's the abbreviation of compact opening louver with variable thermo-optical properties. Quickly the outline of this presentation, so I will introduce the project, then I will explain the design, sizing, and manufacturing phase of the project. After that, I will jump to the preliminary test of the SMA, then the integration of the SMA in our mechanism, and I will finish with the system validation and a conclusion. So, the cooler project is a European it's a project from ESA, so it's the European Space Agency, and its goal is to design and test a louver for CubeSats or compact instrument. So if we take the example of this satellite, the louvers are there. They are placed on the external surface of the satellite, and it works like that. So when the inside of the satellite is cold, the louvers are closed. When the inside of the satellite is hot, the louvers open in order to cool the satellite. And in our project, we used shape memory alloy to make this opening and closing motion. There are different characteristics of our louver on this slide. I think the most interesting is the next one. So the design phase, the assembly phase, and the major part of the tests of this louver were realized at Cscm and by Cscm. And about the shape memory alloy, its sizing, its manufacturing, and its characterization were realized by a supplier, of course in a collaboration with Cscm. So, more specifically, our louver is composed by two actuators, one shape memory alloy, and the other one is a bias spring. These two actuators are physically fixed on the base plate of the louver, and these actuators can deform two flexible grids. You have an example here, and the deformation creates the opening and the closing motion. So maybe it will be easier to understand with the short video. So this is a flexible grid, and when we apply a force on it, the grid deforms, and without this force, the grid comes to its original position. Now we can have a look at this new picture. So in cold configuration of the louver, we use the force of the bias spring to make the louver closed. So in green and yellow, you can see the flexible grids, and the mechanism is closed. Now, when in hot configuration, now we use the force of the shape memory alloy actuator to open the louver. And in this configuration, both grids are hidden under the black one, and the mechanism is open. Maybe I'm repeating what I told you before, but both actuators are physically fixed on the base plate. So it means that for the shape memory alloy, that the shape memory alloy is activated by thermal conductivity and not a radiation in our case. On this slide, there are a lot of different information, but I think the most interesting are the first bullet. So here you can see all the SMA sizing criteria that we used in our project. So there are the stroke, the force, the lifetime, and the material, transition temperature, and the dimension of the actuator. The three criteria in white are the ones given to the supplier. The three others in yellow are the ones that the supplier can play with to achieve the requirement. In our project, it was really complicated to achieve all the specification for the shape memory alloy actuator, because these 6 criteria are linked together. So in our case, we had to find best compromise for each criteria. In general, during prototyping phase, the risk of discrepancies between the requirement and the effective specification should be mitigated to avoid problems during SMA integration in the mechanism, for example, and the performance tests. What I mean is, for SMA prototype, it can, or an SMA prototype can not match 100% with the specification that you need for a prototype. In our case, we had to size and manufacture several iterations to obtain more or less what we wanted. This is the preliminary test slide. So after the SMA manufacturing and before the integration of the actuator in our mechanism, we did some preliminary tests. So here the idea was to find the best model for our applications. So we designed a simple test bench, and we characterized all the manufactured actuators. Our idea was to characterize the transition temperatures, the stroke, the force, and the dimensions of each actuator. Thanks to this little test bench, we highlighted some problems with the actuators, and with the different iterations, we solved it. About the integration of the SMA in our mechanism, I don't have a lot of things to explain, because it was not really complicated to introduce this element in our mechanism. One more time, for a prototype, your expectation must not be too high. In our case, all the manufactured actuators were longer than expected. So for a small mechanism like that, we had to remachine some parts to assemble correctly the louver. I think this part is the most interesting because it's the test part of the presentation. So the test campaign of this louver was divided in two parts. The first part is on this slide. So here the objective was to test the functionality of this louver at ambient temperature. As you will see in this short video, we heated the SMA with a hot air gun. And as you can see, the louver opened. And now it's slowly closing. And now it's perfectly closed. The second part of our test campaign was this one. So here we placed the louver in a thermal vacuum chamber, and the objective was to test this louver under vacuum. In a few words, the base plate of the thermal vacuum chamber made some cycles from cold to hot temperature. And it means that the base plate of the louver and also the SMA actuator heated and cooled, and this temperature changed created the opening and the closing motion of the louver. We placed some thermal sensors on the louver to monitor its temperatures, to check the opening and the closing stroke of the louver. We engraved some targets on the flexible grids, and we also used a camera and a light system. And we covered the full mechanism with a MLI blanket to insulate it from the radiation. So here you will see one cycle of the louver in the thermal vacuum chamber. So normally, yes, it's opening, and after that it will close. Of course, we increased the speed of the video because the full test, we made the full test during 6 or 8 hours, I think. Now it's closing. And next to the video, you have a graphic with all the monitored temperature and the stroke. I will finish with this slide. So, we are currently analyzing the test result of the thermal vacuum chamber test. So unfortunately, I cannot give you a technical conclusion about that. The only thing that I can tell you is, as you saw in both videos, the mechanism seems to work correctly and perfectly. According to our experience in our project, the most complex part of the work was the SMA sizing and the design part of it. As I told you, some iteration were needed to obtain more or less the requirement that we needed. Of course, one more time, this remark is applied for a prototype. Normally for a final product, the SMA manufacturing and the quality of the SMA should normally be increased. I will finish with this remark. So, as users without any background in SMA technology before the project, we had to make quite a big effort to understand this technology from the point of view of the supplier, and also to understand the impact of the different variables. As you understood, the recipe of this shape memory alloy are not really straightforward. That's it for me. Thank you for your attention, and if you have any question, please ask me. Yes.
Like the last, no, before last.
Which one?
This one.
This one, yes.
What's the x-axis?
The x-axis is the time, but it's a bit strange because we have the date and the hour,
Okay.
but it's the time.
Because one of the specific of the shape memory alloy is the time of response.
Yes,
When you
so-
heat it, and I see the symmetry in this one. Something I don't know. But normally, the slope of the heating and the cooling should not be the same, but here is about the same.
Yes, you mean here, the part here.
Because when you heat it, it's rapidly deformed, and when you will cool it and you come back, it takes more time. So slope like that.
Yes, I know. It's the reason why I can't give you any technical conclusion, because we are analyzing this kind of graphics right now. So,
Thank you.
yes?
I think in this case, because the cooling process is slower than the heating process.
It's so useful.
There is this difference, the asymmetry in this curve is due to the cooling and the heating process. Only one curiosity, because why did you choose the copper, aluminum, nickel shape memory alloys?
To be honest, I don't remember, because I began this project and all the discussion about these materials.
It's closed.
Yes.
The materials is
Yes, but what I remember is we changed the material in the middle of the project because of these 6 criteria. I don't remember why, but at the beginning we had one material, and it doesn't work, I think, because it doesn't work for the force and the stroke or something like that. And after we had some discussions and we changed the material. It was a suggestion from the supplier, and we chose this one. Of course, maybe an additional information about this part of the project. To be honest with you, we had a lot of meetings and discussion with the supplier to achieve more or less what we needed. Because when the stroke was correct, the lifetime was not correct, and after when the lifetime was correct, the force was not correct. So it was quite a nightmare at the beginning.
Okay.
It's not TSS, I hope.
No.
Good to point out.
No, we know them.
We know them.
So did the supplier give you any information about like the different phases of the alloy, how it was composed to each other, like the copper, aluminum?
I have information about that, but not here.
Okay.
here the idea was really to explain our feeling with that, because at the beginning of the project, I didn't know that shape memory alloy existed. So
Okay.
I began from zero.
All right.
Perfect.
Thank you very much.
Thank you.
So after this journey from starting with the theoretical basics, and we saw what was developed in this Sma project, with also applications from the industry, and then applications from Cscm, and a point of view from someone who applied SMA for the first time. I think if we look at the time, we should go for the apéro now. And then the room is still open, then maybe have a look at the different demonstrators. You can take also your drinks in here, but not the food. That's how it works. So I guess we'll go to the apéro right now.